Today we will be presenting Recovery RL, Safe Reinforcement Learning with Learn to Recovery Zones. This work is in collaboration with researchers from UC Berkeley, Google, and Stanford. Reinforcement learning provides a flexible approach for policy optimization, which has seen recent success in a variety of robotics domains. During RL training, agents actively explore the environment to discover high-performing policies with respect to a reward signal. However, learning new tasks involves sufficiently exploring the state space, which can lead to unsafe behaviors during learning that lead to constraint violations and inefficiencies. In this paper, we study how exploration can be constrained to regions of the state space where safety is probable. We begin by defining unsafe behaviors. A transition is unsafe if it indicates an undesired behavior we do not want to encounter during online exploration. Behaviors in practice can be considered undesirable if they break the robot or its surroundings, which can lead to a real-world cost in terms of money, resources, and human effort. We assume that the environment provides evaluations of a constraint cost function, which indicates whether a state action tuple is constraint violating or unsafe. This is similar to how MDPs typically admit evaluations of the reward function as the agent interacts with the environment. There is significant recent work in deep RL literature that studies jointly optimizing a Lagrangian objective function that incorporates constraint information and task information via a single policy. In contrast, we will present a method that decouples these two objectives across two RL policies and uses a learned set of safe states to switch between them during online exploration. There is also significant recent research on constructing safe sets in the state space to limit exploration to safe regions, including at ICRA today. In several of these works, safety during exploration and policy improvement can even be guaranteed under additional regularity assumptions. In this work, we formulate a safe set that probabilistically reasons about the ability to recover to safety and also learns a policy that learns to recover. We will be working in the Constrained Markov Decision Process, or CMDP framework, which is a popular extension of MDPs to incorporate constraints. We let S denote states, A denote actions, R denote the reward function, and gamma denote the reward discount factor. Typically, the goal in unconstrained RL is to find a policy pi that maximizes the expected sum of discounted rewards, which we will denote by R superscript pi. In the CMDP framework, we again maximize R pi, but only over policies that are considered safe. Policies are considered safe if their discounted sum of constraint costs is less than the threshold epsilon risk. This involves the introduction of three new components to model constraints in safe policies: the constraint indicator function, C, constraint discount factor, gamma risk, and the constraint tolerance, epsilon risk. Setting the constraint discount factor, gamma risk, to 1 results in a robust optimization problem. Safe reinforcement learning is a promising approach, but in order to avoid unsafe behaviors, an agent must still experience them to learn what they look like. However, this can conflict with task-driven exploration, as the agent needs to explore in order to perform the task well. To address this, we propose providing a few demonstrations of unsafe behaviors in the environment. This is analogous to a human showing a robot that tipping over glassware is undesirable by gently tipping over a glass. The goal is to avoid discovering that this is unsafe behavior during online exploration, where the robot might discover this by knocking the glass off the table, shattering it. We use this data to learn a safety critic, Q-hat risk, which estimates the discounted future probability of constraint violation under the current policy. We visualize Q-hat risk with a heat map in which blue regions correspond to low probability of constraint violation, and colors closer to yellow correspond to a high probability of constraint violation. In the domain illustrated here, collisions with the maze walls or boundaries are considered constraint violations. This brings us back to the original optimization problem. We want to find the policy that maximizes expected discounted reward such that the discounted probability of future constraint violation from the start state is below the threshold epsilon risk. As mentioned before, Recovery RL will learn a task policy that optimizes the task reward, and a recovery policy that is trained to prevent the task policy from violating constraints. Online, the safety critic will serve as a gating function to select which policy to execute based on the current estimate of risk. We define the safety critic for a policy pi to be expected discounted sum of constraint costs. Because we use indicator functions for constraint costs in this work, this is equal to the discounted future probability of constraint violation. Because system dynamics, rewards, and constraint costs are unknown, we train a parametric estimator to learn this value from sample trajectories. The estimator is a feed-forward neural network that is trained with a Bellman backup loss as in standard value function learning literature. We then use the safety critic to define a recovery policy. The recovery policy is also an RL agent whose sole objective is to minimize the safety critic and therefore maximize safety. The recovery policy can be trained with any RL algorithm, and we will present both model-free and model-based recovery policies. The model-free recovery policy is trained via gradient descent on the safety critic, similar to DDPG. The model-based recovery policy learns a probabilistic dynamics model and plans over the model over an H-step horizon, minimizing the sum of the safety critic values along the planned trajectory and taking the first action in the trajectory. In summary, Recovery RL initially leverages a set of offline data of unsafe behaviors provided by a human or hand-coded policy to initially see the safety critic and recovery policy. During online execution, at each time step, Recovery RL first samples an action from the task policy. The safety critic is evaluated on this action and the current state. If it exceeds epsilon risk, the recovery policy is executed. If it is less than epsilon risk, it executes the action from the task policy. We evaluate Recovery RL on a set of simulation and physical domains to test whether it can effectively trade off between task-driven exploration and constraint satisfaction during online learning. Because we want to capture these potentially conflicting objectives, we report the ratio of cumulative task successes to cumulative constraint violations. We report both cumulative task successes and cumulative constraint violations separately in the appendix of the paper. For the task policy, we use soft actor critic, and for the recovery policies, we use DDPG and PETs, as mentioned previously. We compare Recovery RL to 6 baseline algorithms that are built off state-of-the-art current methods that consider constraint violations and task performance in a single objective function. For all reported results, we present the mean and standard error across 10 random seeds. We evaluate Recovery RL on 6 simulation domains, including 2 context-rich manipulation tasks and 1 visual navigation task. In the navigation domains, the goal is to navigate to a goal configuration without bumping into walls or obstacles. This is challenging because the agent must explore the state space widely in order to locate the goal configuration, and in the non-image-based environments, the agent only has access to its position. This means that it is blind to the walls in the environment, and it must learn their positions from experience entirely. In the object extraction tasks, the agent must push the yellow block slightly out of the way in order to grasp and extract the red target block. The block positions are randomized, and the agent must balance safety and exploration because it must carefully push objects without knocking them over in order to be able to complete the task at all. Constraint violations occur if any block is knocked over or if the arm bumps into another dynamically moving arm in the workspace. We find that model-based Recovery RL, shown in dark green, outperforms all baselines on all tasks. We hypothesize that the model-based recovery agent is able to perform well because recovery can usually be achieved over a short planning horizon. The model-free Recovery RL algorithm, shown in lighter green, also outperforms baselines on the navigation domains and comparably to the best baselines on the object extraction tasks. As an illustrative example, we see that the safety critic and recovery policy are able to protect the agent during different stages of exploration in the maze environment, where the goal is to reach the center of the rightmost column without colliding into the maze walls. Again, since the agent only has access to its position, it must learn the positions of the walls from experience, as they are not directly observable. We also evaluate Recovery RL on an image-based obstacle avoidance task on the DaVinci Research Kit, where the goal is to guide the end effector to the goal configuration without bumping into any of the red obstacles in the workspace. Visual servoing is a popular recent approach to accurately commanding surgical robots, as they can have positioning errors due to their cable-driven arms. This task simulates moving around delicate tissues in the body using only visual cues. We again find that model-free Recovery RL, shown in light green, outperforms baselines on this task, and that the recovery policy is able to guard the agent against collisions during online exploration. We will now discuss limitations of Recovery RL and potential avenues for future work. First, while Recovery RL does not require offline data of unsafe behaviors to work, it significantly benefits from access to them. However, even if a human is carefully providing these demonstrations in a controlled way, this can still be expensive to provide. In future work, we will study how to leverage data from different robots and tasks to learn a transferable measure of safety using meta-learning, in order to minimize the number of demonstration samples required to provide a good initialization for the recovery policy and safety critic. We also note that the CMDP framework used has hyperparameters such as epsilon risk to model risk tolerance. While our ablations suggest that Recovery RL is not very sensitive to epsilon risk, finding an appropriate threshold still requires tuning in order to make sure that the agent appropriately balances safety and exploration. In future work, we plan to study how to adaptively set this balance based on the current rate of learning progress and constraint violations. Additionally, we will study how to provide safety guarantees for this method in future work with additional assumptions. In summary, Recovery RL is a safe RL algorithm that splits safety and task performance across two separate RL policies and uses a safety critic to switch between them during online exploration. Recovery RL can also use offline demonstrations of unsafe behaviors to seed these functions to further prevent constraint violations during online exploration. We would love to answer any questions or chat more about this work and possible collaborations, so please feel free to email us and check out our website.